Welcome to the 52nd lecture on computational mathematics with CS Math. In this lecture, we will look at two things. One, in case you have higher order differential equation with initial conditions, how to convert this into a system of first order differential equations. And the second, we will look at algorithm which is known as fourth order Runge-Kutta method for solving initial value problems. So, let us start with an example. So, suppose you have a differential equation x double dash minus 4x dash minus 5x equal to 0, that is a homogeneous second order linear differential equation, and where x 0 is equal to 0, x dash at 0 is 1. We want to convert this into first order linear differential equations, that is a system of first order linear differential equations. So, how do we do that? Let us assume x1 to be x and x2 to be x dash. In that case, what we have, first equation is, if you look at x1 dash, that is x2. So, that is the first order differential equation, and the second, let us look at x2 dash. What is x2 dash? x2 dash is x double dash, and which is equal to 4x dash plus 5x from this given equation. Therefore, we have two equations, namely first is x1 dash is equal to x2 and second one is x2 dash is equal to 4x2 plus x1. So, this is a system of first order linear differential equations, and now let us look at the initial conditions. Initial condition x 0 is equal to 0, but x is x1, therefore x1 0 is equal to 0, and x dash 0 is equal to 1, therefore x2 at 0 is equal to 1. So, this is a first order linear differential equation, system of first order linear differential equation, which is obtained by this second order linear differential equation with these initial conditions. If you have third order, you will get 3 equations in 3 variables and so on. So, in case you have nth order linear differential equation, then you can convert this into system of n first order linear differential equations. Okay. So, let us look at how we can solve this system, and we will see that when we solve this system or we solve this system of first order equations, they are the same. So, let us look at. So, suppose we want to solve this system using DE underscore solve. We have already seen that we can solve such linear ordinary differential equations using DE solve underscore system, or we can solve this using method of diagonalizations. We looked at a few examples as an application to eigenvectors and eigenvalues, right. So, if we what we are doing, we are taking t to be variable x1 and x2 as a function of t, define the first differential equation, that is x1 dash is equal to x2, second differential equation which is x2 dash is equal to 4x2 plus 5x1, and then solve this. So, when we solve this, you can see here the x is nothing but x1. So, if we try to print what the solution we have obtained, just a second, it is taking little bit of time. Yeah, it has come. So, x1 t is equal to 1 by 6 e to the power 5 t minus 1 by 6 e to the power minus t. So, this is the solution of this system of first order linear differential equation. Now, in case you try to get solution from this x2 is equal to this, then you can, since x2 is x dash, integral of x dash will give me x. So, therefore, if we integrate x2 we will get the solution, right. So, this is again the same as x1 t, which is xt. Now, the same differential equation, suppose we try to solve using inbuilt function DE solve. Now, this time we are solving the second order this initial value problem. So, again declare x t as a variable and x as a function of t, declare the differential equation, that is second derivative of x minus 4 times first derivative of x minus 5x is equal to 0, and when we solve this with initial condition x 0 is equal to 0, x dash 0 is equal to 1, this is what we get. This is same as what we obtained using solving system of first order linear differential equations, right. So you can also use inbuilt function which is Euler's underscore method 2 cross 2. So SAGE has inbuilt function to solve a system of two linear equations in two variables initial value problems using Euler's method, and this is what is called Euler's underscore method 2 cross 2. So how do we do that? First you declare this field, a real field, and then declare x t x y as variables. So these are the polynomial over polynomial rings, and the generators will give you t x y, and then define the function f, and then let us apply this method Euler underscore method 2 underscore 2 cross 2, and then when we apply this is what we get. So in this case it will report the value of t's. So here we are taking t initial value as 0, final value as 1, and the step length is 0.1. So you can see here 0, 0.1, 0.2, and at this value giving value of x, value of y, it is also reporting h times fx ft xy and h times gt xy. So this is again very similar to Euler's method. So in this case of course you can ask how these things have been obtained. So this is quite simple actually. One has to apply this Euler's method to each of these coordinate equation, that is x dash t and y dash t. So and then you just put this in a matrix form, right. You can also try to plot the points which we have obtained. So there is a inbuilt function Euler's underscore method underscore 2 cross 2 underscore plot that will plot also this set of points. So I will leave that as an exercise for you to explore. Now let us look at this fourth order Runge-Kutta method, or popularly it is known as RK4 method. So this is algorithm which is very efficient and quite popular, and if you looked at last time we looked at the error, we compared error in Euler's method and Euler's modified Euler's method, and what we observed was that the error is somewhat linear. So it is not very efficient method, whereas RK4 method error is much smaller and it decreases quite fast as you increase the number of as you decrease the step size. So let us look at what is this method. So this method, what we want to do, we want to solve this dy dx is equal to fxy, and initial condition y at 0 is y0 y naught using fourth order Runge-Kutta method, and okay. So this actually involves computing slopes at 4 different points, so 4 slopes, and taking weighted average of these slopes. So we saw in case of Euler's improved Euler's method, we took average slope at xi yi and xi plus 1 yi plus 1. In this case we take 4 points and we take the slopes and find the weighted average, right. So these 4 slopes, let us call this as k1, k2, k3, k4, and then what is this k1? K1 is the slope of y at xi yi, k2 is slope at xi plus h by 2, half of this step length, and yi plus h by 2 times k1, k1 is this. Similarly k3 is f of xi plus h by 2, again at half of the step length, comma yi plus h by 2 times k2, and k4 is slope at f xi plus 1, that is xi plus h, and yi plus 1, which will be yi plus h times k3, right. So and then we take yi plus 1, define the next iterate, the next approximation as yi plus h by 6 times k1 plus 2, k2 plus 2, k3 plus k4. One can think of also this, one can also obtain this using Simpson's rule, but this is just a weighted average of this K1, K2, K3, K4. Now if you look at geometrically, let me just show you what is geometric meaning of this. So here let me make it small so that it fits in the window. So what is it here? This is this blue curve is y equal to t, and this is a point, initial point t naught. This is t naught plus h by 2, t naught plus h. So what is at t naught you have y naught here, that is the and k1 is the slope at x naught y naught, and this is k t naught plus h by 2, that is going half of the step length, and then this is your point here. This is y naught plus h times k1 by 2, and this is the slope k2. This is how you define k2. Similarly, you take y naught plus h k2 by 2, and at this point you define the slope as k3, and then you have this point which is y naught plus h k by 3 at t naught plus h, and then you define the slope k4, and then take weighted average of these k1, k2, k3, k4. So that is how geometrically it is defined. This particular graph is taken from Wikipedia, so I must admit that. Okay, one can draw this very easily in Sage Maths as well. Okay, so let me close this and get back to the worksheet. So this is how we defined this iteration scheme of RK4 method. Now let us implement this in Python. So it is again very similar to what we have done in case of Euler's method and improved Euler's method. So here we are giving the name RK4. Inputs are f, x naught, y naught, and then the step size, and then the end point at which you want to evaluate, that is x1, and find out what is the n number of interval in which we are dividing this number of the intervals, sub intervals in which we are dividing x naught to x1, and this is the solution you start with initially as x naught y naught. Xy you initialize as x naught y naught, so that instead of calling xi yi, we will simply look at x and y. So k1 is f at xy. Run the loop I going from 1 to n plus 1, because the last one is xn. So this range will give you 1 to n, and then define k2, which is f at x at plus half of h plus y plus h into half h by 2 into k1, similarly k3, and then k4, and then define y is equal to y plus 1 by 6 into h times k1 plus 2 k2 plus 2 k3 plus k4, and then increment x by x naught plus ih, that will become the next node point, and then everything you append xy which you have obtained in the solution list, and then return solution, right. So that is this is a simply a Python program, and now let us use this to solve a differential equation. D by dx is equal to y into y minus x divided by x into x plus y. This we have already we solved in last lecture. So let us look at the same problem, and we are starting with x naught is equal to 1 and y naught is equal to 1. So y at 0 is 1, and h is step length is step size is 0.1, and x1 is 2. So between 1 and 2 you want to find value of this yi, approximate value of yi using RK4 method. So let us call this method and store this set of points in capital T, and now we can plot, we can tabulate this, the xi and yi, and these are the value, approximate value of yi. The last value is 0.8767, right. So and let us use inbuilt function. So Sage, we saw that Sage has inbuilt function called desolve underscore RK4. So let us call this method. So fxy, you want to solve with respect to y. Initial conditions are 1 1, that is y at 1 is 1, end points is 2, step size is 0.1, and then when you again tabulate this value, we should obtain, just a second, it takes, okay, now it has done. So, when we tabulate this value and if you try to compare this with what we have obtained using our own user defined function, it is pretty similar, right. So, this is how you can make use of inbuilt function to solve using RK4 method, right. And in case you have higher order differential equation, you need to convert it to the system of first order linear differential equation and then you can solve, right. Okay. So, let us try to solve this analytically. When we solve this analytically, then the solution which we obtain is given by this implicitly defined function, which is x into e to the power minus half is equal to e to the power yx by 2x minus half into log of yx by x. So, if you try to plot graph of the solution curve, which is the exact solution using streamline plot, we have again seen this, how we can plot the solution curve or integral curve passing through a particular point. So, in this case the point we are taking as 1 comma 1, which is y at 1 is equal to 1, and then plot this t, the set of points which we obtain using our own user defined function. You could also use the t1, which is solution obtained using inbuilt RK4 method. So, when we plot this, you can see here this red curve here is the exact solution, and no, this the blue one is exact solution and the red one is the approximate solution, and approximate solution and blue solution curve, they are very close to each other. In this case they are almost matching, right. If you increase the step length further, then if you decrease the step size further, then you will get much better approximation. Now, let us compare all these three methods which we have looked at, namely Euler's method and modified Euler's method and RK4 method. So, let us try to plot a graph of a solution curve using these three methods with a different step size and then see how they compare. So, first of all, what we will do, we will store these user defined functions we have defined, namely RK4 method and earlier two method in a function or in a file which we have called as de underscore method and dot py. So, these functions I have stored it here. So, we saw that how to create a Python module. So, this is what is done, these three functions are stored in this. So, let me close this file. So, all I have done is I have copied these functions which we have created in de underscore method dot py is extension, and then let us call this three functions. So, first let us import de underscore methods, all the functions inside this, and then what do we do? Let us look at a differential equation dy dx is equal to fxy, which is where fxy is minus 2y plus 2x cube into e to the power minus 2x. Again we solve this problem in last lecture, and we start with initial condition x0 is equal to x at x0 is 0 and y0 is 1, that is y at 0 is 1, and h, the step length is 0.05, x1 first let us start with step length 0.1 and the end point is 2, and then let us plot the first the streamline plot, that is the exact solution obtained or the solution curve passing through 0 comma 1, and then T1 is obtained using Euler's method, T2 is set of approximate solutions obtained using modified Euler's method, and T3 is using RK4 method, and then let us plot these set of points which we have obtained for Euler's method in red color, modified Euler's in black color, and RK4 method in green color, and let us ask it to show. So, let me reduce the figure size. So, let me say fig size is equal to 5, and let us plot this. So, when you plot this as you can see here, this blue one is the exact solution, and this the green one is using RK4 method, which is much closer to other two. The red one is Euler's method and the black one is modified Euler's method. So, again you can see here modified Euler's method is much better than Euler's method, whereas RK4 method is better than these two, right. And if you try to reduce the step size, for example, let us make it 0.05, the half of the 0.1, and then when you plot, you can see here now it has become much better, the approximation is much better, right. So, this is how these two methods, these three methods compare with each other. I also expect, or rather I will suggest you to tabulate the error term with Euler's method, modified Euler's method and RK4 method. We already did tabulating error terms, errors in a tabular form using Euler's method and modified Euler's method. In that you also add in the next column, which is RK4 method, right. Okay. So, let me leave you some simple exercises. So, the first exercise is convert this second order linear ordinary differential equations with this initial condition in a system of first order ODE, and then solve it using D_solve systems, and solve this system using RK4 method with step size h is equal to 0.14. Here the initial condition is y at 1 is equal to 4, and so you need to find or need to approximate this y between 1 and 2 with step length 0.14. Next one is again solve this using RK4 method with this step size. This is here the function is slightly different, and the next one is again solve this using RK4 methods. So, these are pretty simple exercises, and once we have developed this user defined function. So, of course, in all these things you should solve this using inbuilt function and also compare it with your user defined function. Okay. So, let me stop here, and in the next class we will look at how to solve system of non-linear ODE. Again we can use inbuilt method using RK4 method, and we will also try to create our own function, and then we will look at also some application of this. Okay. So, thank you very much. Let me stop here.